So the next presentation, we have Olga Stewart from Geosyntec Consultants here in Anchorage. And her work focuses on characterizing contamination in the environment, soil, water, air, and figuring out the risk to human health based on that, and then coming up with solutions for those, for that contamination. And I actually met Olga in 2018 when Geosyntec Consultants was actually doing a project for the council that you'll recall with the secondary containment liner at the terminal. So I called in a favor for her to come talk to us tonight about her subject. So thank you, Olga.
Very happy to do this favor. So I think all of us here tonight are interested in preventing harm to the environment, which is what I think of as kind of the goal of the remediation practitioner. Although I hope that we never get there in the first place, because we want prevention in the first most way, I think, mostly prevention. And then if we have the unfortunate event of some sort of a spill or release to the environment, then remedial practitioners like me would come in. So just kind of talk a little bit about remediation in general. I think of it as a whole host of different options that we can choose from to try to help remediate what's happened in the environment. And it can be things like physical options, like capping something or putting up a barrier to prevent access. It can be things like chemical responses where we use some sort of an agent like an oxidant to, for lack of a better term, neutralize the issue. We can use biological response like a microbes or bacteria to try and deal with something that's released in the environment. And then thermal, we're using heat, which is what I'm going to be talking about this evening. So Geosyntec Consultants, the company that I'm with, we're sister companies with this firm called PFAS Solutions, which was started about 10 years ago to explore the research in bringing smoldering combustion to the remedial environment. So that is what we call STAR, self-sustaining treatment for active remediation. And that's what I'm going to be talking about this evening. So this is a fairly recent technology. It was only about 10 years ago that we put the first pilot study for STAR in place. And you'll see STAR and STAR-X are both listed on here. STAR is what we call the in situ, in the ground treatment, and STAR-X is the ex situ, where you've already dug some dirt up and you're dealing with it above the surface. So this is a pretty recent adaptation from the research environment to full scale. And only about 5 years ago did we actually start doing the first full scale application of STAR. It was a site in New Jersey, which I'll talk about tonight. And we just wrapped that up this year. And at this point, there's about 50 different sites worldwide that we've used STAR on. So this is going back to sort of a grade school fire triangle and how it works. You need heat, air or oxygen, and some sort of a fuel source, which in this case, the fuel source that we're using is a petroleum, most likely. And this works the best on heavy end petroleum. So the crude oils, the bunker fuels, some of the fuel oils, the coal tars. It can work on diesel or the middle distillates and even the lighter ends, but it's not as effective. So the smoldering technology, kind of like the briquettes of charcoal that you're used to, in order to propagate, you need that slow, long burning combustion to occur. And so what happens is after combustion, we get carbon dioxide and water. And if it's incomplete combustion, right, we get some byproducts. So this is a, you might have to actually click on this. I don't know if I can do it. This is a animation video that will just kind of walk us through the process of in situ STAR. So what you're looking at is that hole in the ground is the injection point or ignition point, we call it the IP. And that hole has both air injection and also the heater in it. The thermocouples that it just said show the heat and show the temperature as it's propagating. And then you have air vapor extraction, right, through a treatment for, so that you collect any of the vapors that are produced from incomplete combustion. So as the air is transporting over the heating element is electrical. It starts that fire triangle, right? So you have air, you have the heating element, and then you have this dark brown layer, which is the contaminant, some sort of a fuel in the ground. And once it reaches a critical temperature, that will actually start to ignite and smolder, and you can turn the heating element off. So that's an important piece about this technology, is that it doesn't require sustained electrical or heat energy input. Once it starts, it'll self-propagate. So this is propagating across, and the important piece is if you have enough air, you have enough fuel, and you have enough heat, then it'll continue to propagate out to what we call the radius of influence of this particular point. And at that point, the smoldering will arrest and combustion will stop naturally. And then you'll move on to the next ignition point. So there'd be many of these ignition points at a particular site, each one treating a small radius. So within like a bunker C or a heavy, like a crude type of a site, you'd probably end up somewhere around 10 feet as the radius of influence. It's really a function of your soil types, you know, what your airflow can be through that, how deep you're looking, what type of fuel, all those types of things. So for the most part, you always need a pilot study to figure out what your radius is that you'll be working with. And so this is just the explanation again about the difference between STAR and STAR-X. And so STAR you would do in situ below the ground. You'll probably notice on the animation in both here that you can do it underwater. This is also a little bit different than other thermal technologies because in this case, the combustion is happening at a high enough temperature that the water is vaporizing as the front propagates. So it's not a problem to be under the groundwater table for STAR to function. And then STAR-X is really great if you have something shallow or already dug up, a pile, or if you have a lighter end fuel and you would want to combine it with a heavier end fuel to sustain propagation longer. So I'm going to run through 3 case studies tonight now that you kind of have a basis of how this whole thing works. The first one is on STAR, the in situ technology. This is on the site in New Jersey that I mentioned started 5 years ago and just wrapped up this past year. It was the first full-scale application done in connection with DuPont. It is 37 acres in Newark along the Passaic River. And they had both shallow and deep coal tar at this site. So I'm going to run through this animation again so just show you what it looks like in real life. So this is what the in-well heater looks like, electrical heater. It's about 3 to 4 feet long that goes down the hole. This is what that actual well connection looks like at the surface. So you have the heater running through that, but also airflow. And so this is what the air manifold looks like coming off the side of the trailer. And you'll see there's about 10 points here. So one trailer can service about 10 of these IPs, the ignition points at one time. So you'd set them, 10 feet apart if that was your radius and run them all sequential or at the same time simultaneously. This is what the treatment trailer looks like that's running all your DAC. And this is for the vapor extraction for any of those incomplete combustion volatiles that come up through the soil. So you're collecting them before they get to the surface and running them through a treatment. In this case, it was a thermal oxidizer was what was needed to successfully treat that before the air was released to the environment. So this is what it looks like at the surface. The big yellow tubes are the vapor extraction going to the treatment system. It's kind of hard to see, but they're the skinnier kind of red and black wellheads are your ignition points for the air and the heater. And then there's also thermocouples, which I haven't talked about that much, but thermocouples are placed within the radius of influence to track how that smoldering front is occurring so that you can get a sense of when it's finished. And it's also, you can see in the back there, protective for utilities or other underground things that are there that you want to make sure are not going to be affected by the front. And then this is what it looks like running to the trailer. So the way that we know whether this is working or not is really easy on these heavy end fuels, which are really dark colored, like black coal tar in this case, or heavy crude. And so this is a really nice thing about this technology, is it just visually shows you that you went from this dark fuel to that nice iron oxide kind of look, burned soil. A couple other examples, it looks the same. And so this is kind of what that treatment would look like across the site with, I think there's somewhere around 500 holes put in place, and each one was smoldered to its radius. And at this point, the time that we put this map together, it was about 80% done. That's what the red holes weren't done yet. The green ones all were. And so over time, we removed about 100,000 pounds of coal tar, which is about 12,000 gallons, just on a quick calculation. So next I want to talk about STAR-X, the ex situ version of STAR. And this is maybe slightly more applicable to the terminal, because this was at a terminal in Southeast Asia for Chevron. And they had been using an oil water separator and getting a lot of sludge that needed to be dealt with. And they also had a big pile of just petroleum contaminated soil. And so the two of these were mixed together, partially to control the viscosity issue with the sludge, because it was a little bit too liquid to deal with in the STAR-X unit. So these were mixed together in this mixing containment you can see in the picture. So what this looks like is instead of the heating element going in the ground, the heating element goes in this, what we call Hottpad, and this is a modular unit. So this is one of, that you would have as many as you need to make the batch size that you want. So the strings that you can see are the heating elements, electrical heating elements. And you put these, so this has 6 of those modular Hottpads together with grating on top. And the electrical conduit you can see running into the heating elements. And then also this is the air that's being pushed in as well. So unlike the in situ, both the heating element and the air are put into this system at the ground, and the smoldering front goes up instead of out, like an in situ. So this is what it looks like building on top of the Hottpads. So you put up the sides, and then the top is actually kind of like a chemical hood like you'd have in a lab. And so it's made out of a high temperature canvas, and within that canvas is the air collection system. And on the back side you can see the air comes out through that collection system and goes to a treatment, kind of like the thermal oxidizer we had seen. So back to our mixed sludge and soil. This is what gets loaded into the Hottpad unit. It's a batch process. This one that had 6 of those modular panels put together treats about 300 cubic yards at a time. And then it's covered and loaded and starts the operation. And then this is what it looks like looking from an infrared camera at the thermal profile. So one of the ways to kind of control the energy costs on this is to start one modular Hottpad at a time and then rotate through. So in this upper picture, you can see that kind of this front lower side of the unit is already cool and cooling, and that is done smoldering. And the smolder front is now kind of on that upper right side, which is controlled based on when we started and ignited that smolder. One good thing to note on this is that you can see at the top where the canvas is, it's quite cool, which is good. So this is the similar picture on the before and after for the visuals, that this one had a total hydrocarbon content, 35,000 milligrams per kilogram, that went to non-detect afterwards. We also use other additional lines of evidence beyond just visual, right? Take samples, get them analyzed. For the in situ technology, we can use in situ techniques to get the results as well. So the final case study that I want to chat with you about tonight is treatment of PFAS. So I think probably most of you here are familiar. It's gotten a lot of press lately, but PFAS are these new, not new, but newly interesting compounds for us all to be paying attention to. So the per and polyfluoroalkyl substances, long chain fluorinated compounds that have been used in the environment for all sorts of coatings for resistance to water, resistance to oil, resistance to heat, and that's primarily what we've seen in Alaska. So the state does have regulatory cleanup levels for 2 of these compounds. It's a huge family of compounds, but 2 of them, PFOA and PFAS, we have cleanup levels for in the state. And what we've seen most of the impacts from are from firefighting foam. And it's gone into drinking water supplies is primarily the biggest issue that we've seen. And these don't break down readily over time, and so they're pretty persistent in the environment. So the big question in the remedial side of things is that how do we get this out of the drinking water? And for all intents and purposes, the best technology that has been found so far is no different than your Brita filter, using granular activated carbon to just filter out the PFAS chemicals that are there. So the issue that arises with treatment using carbon is you end up with a lot of spent carbon. So PFAS in general typically causes breakthrough and saturates the carbon more quickly than other contaminants. And so you end up having to use a lot of the charcoal or carbon, and then you end up with it as a concentrated waste stream that needs to be dealt with. So through the Department of Defense environmental research program for remedial technologies called ESTCP and CERTUP, Savron looked at whether STAR would be a good technology to help treat PFAS impacted granular activated carbon. And so what they found was they would apply this in 2 different ways, and these are both hypothetical. They haven't been used in the real world yet. But the idea is that for STAR, the in situ approach, you would take the big impacted GAC pile and actually put it into the subsurface, into a known PFAS contaminated area. So what that does is increases your fuel content in your fire triangle so that the smolder will make it through that entire contaminated PFAS soil zone and remediate that thermally. It also can work et situ, which is you take your pile of contaminated soil, which may be contaminated with PFAS or with hydrocarbons or something, some organic contaminant, and mix it with your GAC stockpile. And so then you have a heavy end, high hydrocarbon content fuel source for your fire triangle, and then put that in your Hottpad batch treatment. So the results of this is again in the lab and not in the real world, but the results were that they took blank soil, dosed it with PFAS. You're looking at 6 different of the PFAS compounds, of which there are hundreds, but 6 of them that are known to be of interest, I guess I would say, and then loaded it with PFAS, which up to a pretty high concentration, I mean 29 parts per million, and then loaded that PFAS contaminated soil with sand and with the granular activated carbon and treated it, and you can see we reached non-detect levels all the way down to the part per trillion range, which is what most people are trying to get to with PFAS, is the part per trillion range. So it was a real successful approach through the research, and so now it's starting to be looked at for other applications. So one of the things that's important about using this thermal treatment versus other thermal treatments for PFAS is that with the GAC as part of the fuel matrix, we can reach temperatures up to and greater than 1,000 degrees Celsius, which is important because that is what shows complete destruction of the PFAS and not just concentration or creation of other toxic byproducts that volatilize off. So that's all I had to chat with you about tonight, and I'm happy to take any questions.
Just a comment here, Rob. I work with the volunteer fire department, and they are the AAA foam for fire fighting foam for airplane, aircraft fires, oil fires. That is not good. So if you guys have any of that in you guys towns or villages, please get rid of it. It's cancerous. So thank you.
Okay, I have a question. So I'm over here as well. So when you're talking about the remediation process for the PFAS and you're basically heat destroying them.
Yeah.
And so what are the byproducts of that? Because you're transforming them. I mean, the PFAS may no longer exist as it once was chemically.
Mm-hmm.
What do you have left over from that?
Agreed. So one of the ways to figure out that you're getting complete destruction of the PFAS chains is if you're getting hydrofluoric acid. And so the research project actually looked at what your concentrations of hydrofluoric acid were coming out to show that you're getting the complete destruction. So that's one of the main byproducts. Yeah, there are others. It just sort of depends on the combustion and kind of what's in your input to start with. But like I had put on this slide, so one of the main things that you're looking for are these volatile organic fluorines. And so the thing about the higher temperatures with STAR is that you're getting less of the volatile organic fluorines than you are in most other thermal processes. But that's typically what you're testing for is the VOFs and then hydrofluoric acid to figure out how complete the combustion is that's occurring.
But do you know what all the other potential transformations are? I mean, matter doesn't, matter transforms, matter doesn't disintegrate.
Agreed, yeah, it's not just going away. I don't have all of the answers for you about that, about all of the different ones. I know what we tested for in this particular research project, but I'm happy to get back to you. Yeah.
I have one here. When you do the burning underground, I missed it or didn't quite understand. How do you sample to tell that you've got all the contaminants burnt out?
Right, so we have to drill back into the soil and pull the soil out to see. That's the main answer.
Okay, just holes.
Just holes. Yep, holes in the ground.
Yes. Back to the question about potential byproducts. I was once involved in a military remediation that was supposedly hydrocarbons, and about halfway through, there was a sudden, oh, wait, we got PCBs here too.
Right.
I don't know what happens to PCBs if you're trying to burn them like this. So the question is kind of an open-ended question. A, what happens when you find something that you didn't know was there? And B, do you know what happens with PCBs in particular if you were using this kind of technique and encountered them?
Right, so PCBs are one of the most persistent chemicals in the environment and very difficult to treat. I don't know the answer to you about what happens to PCB transformation at this type of a temperature. I, again, am also happy to get back to you as well. But in general, the way that we deal with incomplete combustion, right, and other types of contaminants that are present in the soils that are being remediated is to try to capture all the volatiles that we can through the vapor extraction system and through that chemical hood. And each one of the systems has to be designed specifically for that particular site. And so you do this pilot testing and try and figure out what are all the chemicals that we're dealing with, and then design that air treatment system for that particular site. So the example that I brought up from both Southeast Malaysia and the New Jersey site, the DuPont site, both use thermal oxidizers and scrubbers, but the air treatment system is a huge component of the design for this particular system. Mm-hmm.
All very interesting.
I just wanted to comment. This sounds strikingly similar to a technology for in situ reservoir combustion as part of a secondary or tertiary recovery sweep, which, as far as I know, is not allowed in oil and gas in the United States anymore. But second, I'd like to follow up with, when you burn things, they tend to get smaller and more mobile. And I'm curious what kind of groundwater or air quality monitoring do you guys do before, during, and after?
Right. So this New Jersey site actually had a cap across the whole site. I don't know if you noticed on the pictures that where I showed the ignition points and the vapor extraction tubes at the surface. And so it was capped at the surface to try and prevent some of the volatilization that would come through the surface and out to the air. In terms of monitoring, like any remedial process, again, in the design phase, you would look at what chemicals you have, what they're being transformed into, and sort of what monitoring processes are required for that particular site.
I was just wondering about PFAS specifically and potable water, and whether you've been able to ascertain soil that's been treated and the time that it might take to become potable again. You know, that's the big issue up here in some of these towns.
So the time in which you have to remove the water and treat it for pump and treat through GAC?
Probably if this particular mechanism, when you have a finished product, have you looked into the water as far as being drinkable at that point?
Well, right. So the big issue with groundwater contamination is whether it's becoming recontaminated with a source that's in soil or that's being recontributed, right? And so this particular system is dealing with the spent treatment filtration and not so much with treating the water that's already in the ground. I don't know if that answers your question, but it's not necessarily a system that's being used to treat the water itself.
Got to the point yet where you can ascertain if this is going to help clear up areas that are contaminated with this to the point that they could use that groundwater again for potable water systems.
Yeah, I think you're right. I don't think we've gotten to that point yet.
Very promising.
I had a couple questions. One relates to these others about groundwater.
Oh, thank you.
Yeah,
You guys can
right
see me
here.
searching around. Sorry. Yeah, raise your hand. Thank you.
Just we have such variable groundwater activity here, interflow, high rainfall, and so on. I wonder how sensitive the process is, the in situ STAR process. And then my second question is just where this has been proposed in Alaska, like formerly used defense sites or Superfund sites, or and it hasn't been chosen. Why not?
Sure. So, so the first question on would this be successful in treating a source area? I think that's what the question was. And I think that so each one of these sites takes time. So that New Jersey site was a 5-year project. And so if you have a real dynamic groundwater system and I think what you're suggesting is that you've got infiltration from precipitation that's recontaminating your soil at the same time that you're treating it. I know this just sounds like a cop-out to say, but every system has to be designed so that it would effectively work for that particular site. So if that's a real concern, then you might consider something like a rain barrier to prevent infiltration at the time that you're treating, or you might do some other sort of design to try and help with that particular aspect of it. To answer the second part of your question about where this has been proposed in Alaska, so we've been involved in, I think, Ben, you can help me out, 3 pilot studies here, one out on Hinchinbrook Island, one up at Puntella Lake, and one, what's the third? At Eielson, that's right. Ongoing. And at both Puntilla Lake and Strawberry, which are the ones that we really have results for already out on Hinchinbrook, it was a lighter end middle distillate like diesel. And so the radius of treatment came in like around 6 feet. And it was not highly self-sustaining beyond 6 feet. And so for the radius. And so at that point, it's a real question of, do you want to add additional fuel to help make that radius wider, to make it a little bit more feasible, which is certainly the case, or does it just seem like too small of a radius to actually install? And so in both cases, it was the lighter end fuel that sort of made the decision to not go with it. We haven't tried it at a heavier end fuel. The Eielson case is still out. We haven't made a decision yet.
That was interesting. I wonder if the agencies, Department of Defense, or getting objected to the process, and if they did, what were their objections?
Yeah, we haven't, I mean, as far as I know, we haven't heard that yet. It certainly hasn't gotten that far in Alaska, but in the other places that we've implemented this in the United States, it hasn't. So one of the most recent feasibility studies that we did to look at implementing is at Port Kendall down in Washington State. And the EPA just selected it as its selected remedy for that particular facility that's right on the water. And it's currently out in a proposed plan, waiting on comments, but I expect that that's going to be approved.
We have two more questions.
Could you please give us an estimate of the cost of these projects?
You bet. I almost
you.
kept that slide in, but I took it out for the sake of time. Of course, it's economies of scale, like everything, but that 37-acre site in Jersey cost about $70 a yard, a cubic yard. And then the facility in Malaysia, that was a batch process, you know, the 300 cubic yard. And so there's a lot of different things that go into the ex situ, how much your energy input is and all that sort of thing. It's a little bit harder and how much your energy costs. But that one was right around $55 a yard. You're gonna make me do that math. 37 acres, so it was an average of 16 feet below grade. So you can do the math. 5-year project. 12,000 is what we got, yeah. Prevention is the key. 2.5 million. Mm-hmm. It sure is. Every time you're trying to get it out of the earth, when it's in there, it is. Yeah. Yeah, prevention is the key.
And we do have folks listening in via video conference tonight, so try to use the mic. We've got one more question for Olga.
I'm just curious, any long-term observations of, it seems like the byproduct is then it's not contaminated, but it seems very sterile. And so in places where you might want to have vegetation regrowth or you have your organisms in the ground be able to recover and continue the natural processes, have you had any observations of how that happens, or are there steps that you need to do to be able to get it from the sterile, clean state back to a productive?
Yes, actually, that's been another aspect of the research in STAR and trying to answer that question. So I don't think that we have an active treatment site yet that's gone far enough to be revegetated, but in the lab, even the sort of sterile iron oxide, like zero organics left kind of soil still sustains plant growth. And it seems like it is not, what's the way to say this? It seems like it can sustain revegetation without additional amendments required, but you get better growth with additional fertilizer.
All right. Thank you very much, Olga. Appreciate it.